What's up, physics nerds? Here is the video of the 3 worksheets I gave out in class. There's a bajillion problems. Admittedly, these are a little bit on the harder side of what you'll encounter in the quiz, but if you're able to get through these problems, then the quiz should be much easier in comparison. That's a fact. Anyway, let's start. Here we have this circuit. It's a parallel circuit because you see our 2 resistors separated into individual branches, and we gotta figure out the equivalent resistance of the circuit. However, we don't know the resistance value of this resistor, so we cannot figure it out through traditional means. So we gotta go about it in a different way. So equivalent resistance, we should recall, is the overall resistance in the circuit, and we also got these 2 things, the total voltage and the total current. So we're just going to use V equals IR. So REQ equals 2.4 ohms. Alright, that's our overall resistance. Now we gotta calculate the current measured by ammeter A1. If you notice, A1 is placed inside a branch. So that means we're only concerned with the resistance in that branch as well as our voltage staying the same here. So this is again V equals IR. 12 volts doesn't change in the branches. Solving for I inside A1. And we're using our 3 ohm resistor because it's just inside the branch. 4 amps. Now here we're having 4 amps through this part of the circuit. We'd start with a total of 5 amps, which splits up into the 2 branches, 4 amps and 1. That means we have 1 amp left in this other branch, which will help us for the next part of next question. Calculate resistance of unknown resistor R, same voltage. Now we know it's 1 amp, and we could solve for R. 12 divided by 1 is 12 ohms. Now moving on to number 4, you can't really see number 4. Ooh, there it is. So here we have a series circuit. What is the current in the 5 ohm resistor? So in a series circuit, the current is the same throughout, so if you end up using V equals IR with each resistor, you'll get different values. That's not right. So we have to use the overall resistance. Because we are in a series circuit, you just add them up. 9 ohms, 4 plus 5 is 9. Using V equals IR, our voltage is 9 volts. I we're solving for, and 9 ohms here, I is equal to 1 amp. Choice. Next we have a drawing question. It's going to look just like this, like in number 1, 2, and 3. Now, why did I draw it this way? First, they said in parallel, the 2 resistors. That's the easy part. Now this single ammeter placed in circuit to read its total current. So the ammeter has to be placed before the branches in order to measure the total current. If you place it inside, you're measuring the current inside that branch. Now that we got 2 parallel resistors, we can figure out the equivalent resistance using this because it's parallel. I'm going to show you the fraction method. So this is 2 plus 1 over 36 equals 3 over 36. Remember, we got to flip it. 12 ohms. Lastly, we're going to calculate the total power dissipated in the circuit. So P could either be P equals IV, V squared over R, or I squared R. Given that we only have voltage and resistance, we're going to use P is equal to V squared over R. Our voltage is 24 volts. Divided by our resistance, our equivalent resistance of 12 ohms, because we're looking at total power. So we use the overall resistance. You should get 48 watts. Next page, starting with number 8. In which circuit would current flow through resistor R1 but not through resistor R2 while switch S is open? So when the switch is open, you'll see a disconnect in the circuit. So we're trying to disconnect R2 from the current flow. And if you check each of these, the only one that fits the bill is choice 1. R1 still makes a complete loop, but R2 is an open loop because of the open switch. Now number 9. Which circuit diagram below correctly shows the connection of ammeter A and voltmeter V to measure the current through and potential difference across resistor R. Why? Voltmeters have to be connected in parallel to what it's measuring, this one, and the ammeters have to be connected in series to it. So voltmeter in parallel to it and ammeter in series. Choice 4. Number 10, we have to draw a diagram of a battery. Okay, that's our battery. And two resistors in parallel to each other. And an ammeter that reads the total current in the circuit. Alright, so you don't exactly have to place your ammeter before the branches. You can place it right after the branches, as long as it's outside the branches, like this. Alright, number 11. Complete the diagram above to show the two resistors in parallel between points A and B. So parallel has to look like this. We got to create two parallel branches between them. Okay, let's label them. One of them is 15, the other one is 30, and we have a 90 volt battery. Okay, determine the potential difference is the same as voltage across resistor R1. We have a parallel circuit. The voltage does not split up. It's the same in both branches, 90 over here and 90 over here. You could always check the reference table for guidance. Okay, so if it's 90 volts out of the battery, it's 90 volts in each branch. Now we got to calculate the current using our voltage. V equals IR. Solving for I, our resistance R1, 15 ohms, I is then equal to 6 amps. Alright, 24. This is the next sheet. 6 ohm and 4 ohm are connected in series with a 6 volt battery. Let's start with that. 6 ohms, 4 ohms, connected in series in the same pathway. That's what it means. And 6 volt battery, 6 ohms here and 4 ohms here. Last, we need to put a voltmeter to measure voltage across the 6 ohm resistor. So it's got to be parallel to the 6 ohm resistor. Like that. There are other ways you could draw it, but this is one way for sure you could do it. Alright, 25. What is the total current consisting of 6 operating 100 watt lamps connected in parallel? So here we could figure out what is the current through each 100 watt lamp and then add them up because there's 6 branches that all add up to the total current. Or you can make it 6 operating 100 watt lamps. We have a power output of 600 watts. Is our power. Power is equal to I times V. So we have 600 watts is equal to I times 120 volts. I is 600 divided by 120, that is 5 amps. Number 26. What is the total current in the circuit? So we're looking at the big picture here. We need to figure out REQ, equivalent resistance. We have a series circuit, so we just add them up, 4, 6, 8, and 6. That makes 24 ohms. You just add them up, only in series. Now we can figure out the total current using our voltage and our equivalent resistance. 12 volts equals I times 24 ohms. I is equal to 0.5 amps. Number 27. As the number of resistors in a parallel circuit is increased, so if we increase the number of branches, what happens to the equivalent resistance and the total current in the circuit? So if we add more branches, think of it as adding more lanes to a highway. You end up spreading out the traffic, reducing the resistance. So we're reducing resistance. And if you reduce resistance, you end up having higher flow, higher current flow. So we're looking for a decrease in resistance and increase in current. So it's choice 3. Let's pick a different color. Let's go with pink. 20 and 29 is with this diagram with the switch. If switch S1 is open, that means we can disregard that branch with the open switch. So that means our current reading in the ammeter A, we could neglect that one branch. Just use V equals IR. And we're using just a 12 ohm resistor. 2 amps. If the switch is closed, that means we have to account for that branch. So it's parallel. 1 over 4 plus 1 over 12 equals 4 over 12. Flip it. 3 ohms. I'm totally butchering the ohm symbol. 30. Which circuit has the smallest equivalent resistance? So we're looking for parallel. Parallel circuits decrease the resistance. And if we add more branches, we also decrease the resistance. So that's choice 3. Okay, 37 to 39 shows a parallel circuit. What is the current measured by ammeter A? So ammeter A is placed inside the 6 ohm branch. So once again, voltage is the same in each of them, 12 volts, sorry. Solving for I. And we're going to use 6 ohms as our resistor. 2 amps. What is the equivalent resistance of the circuit? You got to use that long string with the fractions. It's 1 over 36 plus 1 over 18. This is equal to our least common denominator is 36. This should add up to 12 over 36, which then you flip it. 36 divided by 12 equals 3 ohms. I just crammed that all in there. 39. How much power is dissipated in the 36 ohm resistor? Power. We have voltage and resistance. So we could do V squared over R. Did I make another order? Oh, never mind. Okay, power, V squared over R, 12 volts squared over 36 ohms. That should give us a power of, that should be 4.0 watts. Choice 4. Number 40, 3 resistors, 4, 6, and 8 are connected in parallel. Equivalent resistance, so we could either calculate it, or you should know right offhand. Equivalent resistance in a parallel circuit will always be smaller than the smallest resistor. Our smallest resistor here is 4, so it's got to be smaller than that. Choice 1. Number 41, a simple circuit consists of these 2 resistors to be connected in a circuit. Determine the smallest equivalent resistance possible. So that means we can either connect these 2 resistors in series or in parallel. If we put them in series, we add them up, 125. Whereas if we put it in parallel, we're guaranteed for it to be lower than 25. So we're looking for that smaller resistance, so we put it in parallel. So we could do 1 over REQ is equal to 1 over 25 plus 1 over 100. Our least common denominator is 100. So this is 4 over 100 plus 1 over 100, 5 over 100. Flip it over. 100 divided by 5 equals 20 ohms, which is our answer. Alright, number 42 to 44 is with this diagram. What is the equivalent resistance of the circuit? It's parallel, so we got to use this again. 1 over 20 plus 1 over 30. Least common denominator we could use is 60. So 3 plus 2 is 5 over 60. REQ is 60 divided by 5, which is equal to, man, I'm drawing a blank here. It's 12 ohms. What is the current reading of the ammeter? So we are inside this branch, focusing on that 20 ohm resistor. Voltage is the same, 12 volts, 20 ohms, 20 divided by 20, 12 divided by 20, 0.6 amps. What is the power in that 30 ohm resistor? P is equal to V squared over R, 12 volts squared divided by 30 ohms. And you should get 4.8 watts. 144 divided by 30, that's about 4.8. Yeah, just about. 45, last question on this page. What is the reading on ammeter A? What kind of circuit do we have? It's a series. So we add them up for the equivalent resistance. 8 plus 8 is, this is a tricky one, guys, it's 16 ohms. Then we can use Ohm's law to figure out the current reading in the ammeter. 12 volts for our overall voltage. I, our total current. And resistance is our equivalent overall resistance. 12 divided by 16 is 0.75 amps. Woo! Even more problems. On this side, we have 46 through 51. Alright. Here we have a parallel circuit. On the diagram above, use the appropriate circuit symbol to indicate a correct placement of a voltmeter. Oops. Let's use a different color. Let's go back to purple. I like purple. Voltmeter to determine the potential difference or voltage across the circuit. So we're looking at big overall picture across the entire circuit. Where can we find the overall voltage? Inside the battery, right here. So that we connect it in parallel to the battery, just like that. What is the total resistance of the circuit? We have a parallel circuit, so we're going to use this fraction equation. 1 over 4 plus 1 over 6. Least common denominator is 12. So we got 3 plus 2 over 12. 12 divided by 5. 12 divided by 5 is 2.4 ohms. There we go. Number 48. Here we got a variable resistor. That's new. It's this little fancy thing. That means you could manually change that resistance in that variable resistor. Alright, at what value must the variable resistor be to produce a current of 1 ampere through R1? So, series circuit, same current throughout. So we need to figure out what's our overall resistance. So V equals IR. 12 volts equals 1 amp for our equivalent resistance. 12 divided by 1. I'd be surprised if you guys didn't get it. 12 ohms. So 12 ohms total in our series circuit. We already know the value of this one. That's 3. How much left is supposed to be here? 9. Because 3 plus 9 gets us our total of 12. So we need 9 ohms in that variable resistor to set a current of 1 amp. Now, number 49. Two identical resistors connected in parallel have an equivalent resistance of 40 ohms. What is the resistance of each resistor? If you remember our shortcut, if we have here 2 resistors of equal value, let's say 8 and 8. If we have 2 resistors of equal value, the shortcut is to take that value and divide it by the number of branches. So 8 ohms, 2 8 ohm resistors, split over 2 branches. 8 divided by 2 is 4. So the equivalent resistance of this particular parallel set is 4 ohms. So here, we can just double 40 and we should get 80. Let's double check. Let's visualize it for a moment. So if we have 80 here, 80 here, 80 divided by 2 branches will get us 40. That's how we know. Number 50. A 6 ohm lamp requires 0.25 amps of current to operate. In which circuit below would the lamp operate correctly when switch S is closed? So when you close that switch, will 0.25 amps run through the circuit. So if we close the switch, that means we have a parallel circuit and our current is going to be divided. When it's open, you could still have a current of 0.25 when it's open, because we only got 1 branch to account for, but when you close the switch, you have 2 branches to split it up. So that's not it. 2. Nope, that's not it. 3 is almost the same thing. The only one that fits the bill is choice 4. You have 0 amps running through the circuit when it's open, but when you close it, you finally get 0.25 amps. Number 51. In which circuit represented below are meters properly connected to measure the current through resistor R1 and the potential difference across resistor R2. So this one has to be in series, and this one has to be in parallel. Alright, we need an ammeter in series with R1. Choice 1 shows it. Choice 3 does not. Look how it's in parallel to R1. That's not it. Choice 2 is not possible either. It's parallel to that as well. Choice 4 shows it's in series with R1. Good. Now we're looking for which of these show the voltmeter in parallel to R2. Choice 1 does not follow. It's in series. Choice 4 is the only one that fits the bill because our voltmeter is in parallel to R2. Alright, finally we reached the last page here. And we're almost at the end of this movie that I'm watching on TV, Aquila and the Bee. I love spelling bees, guys. I used to be a pro speller back in my day. Then math took over. And we all know where I ended up. Anyway, 52. Which combination of resistors has the smallest equivalent resistance? So we need something in parallel. We could ignore choice 1 and choice 4. Those are in series. So let's look here. Choice 2, we have 2 ohm resistors split over 2 branches. So 2 divided by 2 is 1 ohm. Choice 3, 1 divided by 2 branches is 0.5 ohms. So the smallest one is choice 3. Number 53, Kirchhoff's current law. So total current in, total current equals total current going out. So let's pay attention to the direction of the arrows. This is pointing in, this is pointing out, because this center mark is our junction. So these two over here point inward, so that's 5 amps. And the other 3 on the other side point outward, so 4 plus 1 plus 2, that gets us 7 amps. We need these to balance out, the same in, same out. So that means this one over here has to measure 2 amps in order to balance it out. Number 54, what is the minimum equipment needed to determine the power dissipated in a resistor of unknown value? So we don't know what R is. So power we can use as equal to I times V, current times voltage. How do we find current? We need an ammeter. And how do we find voltage? We need a voltmeter, so we need both of those. Do we need a stopwatch? No. We need a stopwatch to calculate energy. Alright, number 55. Series circuit, 10 plus 20. That gets us an equivalent resistance of 30 ohms. Now, what is the current through the 20 ohm resistor? It's whatever current you get here is the same current over here, so we gotta use our overall resistance here. Alright, now we can figure out what's our current using V equals IR. 120 volts is equal to I, we're solving for, and 30 ohms is our resistance. 120 divided by 30, I is equal to 4 amps. You know, Miss McCoy's really sad that figure skating's over. What am I going to do with my life? What am I going to watch every weekend? I don't even know. Alright, number 56. In the circuit diagram shown below, ammeter A1 reads 10 amps. What is the reading of ammeter A2? Alright, so we got 10 amps as our total before the branches split it up. We're looking for the reading of ammeter A2. We don't got much here. But what we can do is figure out what's our equivalent resistance. Because we got a parallel circuit. So I'm going to just show you the calculator shortcut right here. You can plug and chug this in the calculator. And you should get, I think I solved this already before. Yep, this is 12 ohms as our equivalent resistance. Now we can figure out what is our voltage. How do we even figure that out? What current do we use? Well, we got the 10 amps. That's our total current in the circuit. And we also figured out our overall resistance. So we can figure out what's our total voltage. 10 amps times 12 ohms, we should get 120 volts. That's a lot. Think about how many batteries we could use. All right, now we figured out our voltage, so we could figure out what's our current in the branch. V equals IR, Ohm's law. 20 ohms, because we're concerned with that branch. 120 divided by 20 is 6 amps. 57. What is the reading of voltmeter V? So this is series. It's a series. 20 and 10 is 30 ohms. Our current, V equals IR. 60 volts equals I times 30 ohms. I is equal to 2 amps. So 2 amps flows through this entire series circuit. So that way we could figure out what is our voltage drop across that 20 ohm resistor. So V is equal to I times R. 2 amps times 20 ohms equals 40 volts. That's our answer. But let's hold a moment. What is the purpose of this? 40 volts. So in order to get through this 20 ohm resistor, we had to pay 40 volts. We start out with 60 volts, pay 40 here. That means we're left at 20. If you use V equals IR, you could also figure out that you also have to pay 20 volts here. Pay 40, pay 20, so overall you should end up with 0 volts at the end of this resistance path. So that you reach the end of this, go back to the battery, replenish, and start your whole hopeless cycle over and over again. What a poor, sad electron. Okay, so I did all 3 worksheets in probably record time. Hope this was helpful for you guys. Don't study too hard, but I highly suggest you also watch that content review video. You might miss an important gem in there, as is the other gems in this video. Anyway, have fun studying.